This is a asymptotic notations question. We have been given the parameters a and b such that both of them are omega of 1 in complexity, and there is this recursive equation, that is t of n equal to t of n raised to 1 by a plus 1, and the base condition is that t of b equal to 1. So we can formulate this particular recursive equation in this way, that t of n is defined as t of n raised to 1 by a plus 1 for all the values of n other than b, but while n is equal to b, then t of n becomes 1. So this is our recursive equation, and now there can be different methods. We can go for the recursion tree method, or we can just go for the computational way. For example, as we have shown over here, this t of n is given as this particular equation as it was already mentioned, and after that if we go on to recursively apply the same formula upon that, then for this particular expression, if we consider this to be t of m, then that would be further decomposed into the next iteration of t of m raised to 1 by a plus 1, but only the difference would be that this m will again be n raised to 1 by a. So that is what we have written over here, t of n raised to 1 by a, and that again raised to 1 by a plus 1, and this plus 1 originally came here. So this can be simplified to give t of n raised to 1 by a squared plus 2. In the same way, after the third iteration, we get this particular equation, 1 by a cube and 3. So similarly, if we go for k iterations, then in the kth time we get this particular expression, t of n raised to 1 by a raised to k plus of k. So now we will try to accommodate it into the base condition. What is it? That t of b has to be 1. So for that, what we will be doing is we have to convert this particular thing, the parameter, into b. So that is what we have done over here. N of n raised to 1 by a raised to k equal to b. That is what we have evaluated over here. We will take log on both the sides. So that will give 1 by a raised to k log of n equal to log of b. So what does this convert into? We can write 1 by a raised to k equal to log b upon log n. And we know that log b upon log n can be written as log of b to the base n. So that is what we have right over here. So now what we are going to do is we are taking the inverse on both the sides, which means this 1 by a raised to k will get converted to a raised to k, and this log of b raised to n will convert into 1 by log of b raised to n, and this is nothing but log of n raised to b. Both are equivalent to each other. So now we get a raised to k equal to log of n to the base b. These are the basic log operations which we all are already aware of. So that's what we have applied, and after this step we will once again take log on both the sides. So that will give us this power k will come to the front, and we will be left with log of a. So on the left side we have k log a, and on the right side we will have log of this entire equation. So next what we do is we take this k at its own place, and we shift this a to the denominator of the right hand side. So that gives us, it will be log of n to the base b, and this to the base, this on the denominator, there is log of a. So now we will again take this log a from here and make it the base of the upper equation. So that will now become log base a and log of n to the base b. So that is what it will convert into. So we remove the bracket and we are simply left with the value of k as log to the base a, this expression. What is that? Log n to the base b. So that is the value of our k. What is it? Log to the base a. What is the value in it? Log of n to the base b. So now this is what will determine the complexity, or you can say the value of t of n actually. Since a and b both were omega of 1, so we can say that the value, or you can say the complexity of entire recursive equation determined in this particular way gives us this first option, that is theta of log a, b and n, in the same order as we have derived it from there. So this is what first one will give us the answer for this particular question.